I just want to remind you guys, your homework packet, your homework number one, test review number one is due on Friday at the beginning of class. I want you to make 2 copies of this thing. So I gave you guys last time an actual copy of it, so you guys have something to turn in. I want you to do your work on that thing. But also, when you go over to your Canvas site, I made a link right here at the front, right here. So all you got to do is just click on it, and it will actually bring up another one, and you should make a copy out of this one, because you're going to turn in the one that you actually did the work on. And then I want you guys to have a blank copy of it, because we're going to go over this thing actually in class on our Friday class. Now, I know what you're thinking. Oh, no, geez, Dr. Taylor, there's a lot of questions on this thing. Yeah, quite a few of them are short questions. And if you look at those short questions, I put 35 questions on this thing, and trust me, this is way bigger than what your test is going to be. But this is a good idea, and what the test can look at. And that's the reason why I give you these things. Not all teachers actually give you a kind of a homework set that's pretty much just before the test. But the reason why I'm doing this is because I know you guys have worked so much on working on the HALT system, which is absolutely great, getting all the problems done in terms of the computer problems and stuff like that. But, when it comes to a paper and pencil test, we haven't had any much on paper and pencil except for what we've done actually in the notes and the problems we've done in class, which is a great thing to study, don't get me wrong. But I wanted to give you guys kind of a detailed list of what the test questions are going to look like. This is the wording that I'm putting. I'm a guy. I can't change my ways. This is how I worded it on the homework set. This is how I'm going to word it on the test. This is just like it for me. So get used to it. Guys can't change. This is what we do. So once we get a pattern, we just have to stick with that pattern. This is just for us. So I'm signaling to you guys what the test is going to look like. So when you really study this thing in and out, and that's why I'm giving it to you on Friday, and then you've got it over the weekend, and I will record Friday's lecture, of course, going over this thing. You've got something to study over the weekend, so you're well prepared for the test on Monday. Okay? So you've only got, for you guys, 50 minutes on the test. So I'm actually looking at about 20 questions. Okay, that's what you'll be looking at. And it's going to be a combination of multiple choice with free response, probably about 15 and 5 or something like that. I'm a guy. When's the test? Monday. When will I make it up? Sunday night. So, but when I do, this is basically what I'm thinking about stuff. So give you an idea. All right. So just give you a heads up. Last time we were working on these special cases. I call it case number 4. Of limits, and they were a very special case because we were taking the limit as either x approaches positive infinity or negative infinity. Now, I taught you guys also you had the ability to look at these problems and tell what the answer is, but on a free response kind of a part of a test, you got to show me the work, because I don't want just, the answer clearly is going to be a negative 1/4 or something like that. No, I want you guys to actually show the work. So here's a couple of problems. Very much to what we did last time. I just made them up a few seconds ago. So just to remind you, anytime you're taking the limit as x approaches either positive infinity or, here's another one, negative infinity, you're going to do the same thing. Because what we got here is we're taking the limit as x approaches either plus or minus infinity of a rational function, a polynomial divided by a polynomial. And what you do with this kind of a problem is you're going to multiply by both the numerator and the denominator by 1 over x to the degree of the denominator. Your degree of your denominator is going to be your commander. Now, just be careful on something, because sometimes they like to put the classic polynomials out of order, which I did here, but you can look at it. The degree is the highest exponent. So, what is the highest exponent of the denominator in this particular problem here? 3. The denominator, 17 minus 8x cubed, the degree is 3. So I'm going to multiply by 1 over x cubed in the numerator and 1 over x cubed in the denominator. And then you're going to clean it up by distributing this out. So this gives you the limit as x approaches, in this case plus infinity, of, and I'm going to distribute 2x cubed times 1 over x cubed. The x cubes cancel. So I'm just left with 2. Minus 6x times 1 over x cubed. Well, the 6 is going to stay there, but x divided by an x cubed is an x squared in the denominator. So it becomes minus 6 over x squared. Plus 5 times 1 over x cubed, well, nothing's going to cancel, but just get a big fraction, 5 over x cubed. And now I'm going to distribute the denominator. I got 17 times 1 over x cubed is 17 over x cubed minus 8x cubed times 1 over x cubed. The x cubes cancel. What am I left with? 8. Okay? And now, here was the big deal. We talked about this, that when I take the limit as x approaches plus or minus infinity of any kind of number over x to any positive power, when the infinities, whether it be positive or negative, go into the denominator, you with me? The denominator is going to get bigger, but the overall fraction gets quote unquote smaller. This stuff goes to 0. Does that make sense? So when I'm plugging my infinities in, this fraction goes to 0, 5 over x cubed goes to 0, 17 over x cubed goes to 0, and you're left with what? 2 minus 0 plus 0, which is pretty much 2, over 0 minus 8, which is negative 8. And then, of course, you clean up your fraction. 2 divided by negative 8 is negative 1/4. And that's the process of showing the work in terms of a problem where you have the limit as x approaches either positive or negative infinity. But I mentioned to you guys this before, that you can look at these problems if you know your what they call the horizontal asymptote theorem from the college algebra 2 classes from many years ago. Here's the deal. When you got this polynomial over polynomial and you're taking limit as x approaches infinity, you got 3 cases. When the degree of the top is equal to the degree of the bottom, the answer is always going to be the ratio of the leading coefficient. 2 over negative 8 is where your negative 4th came from. So I could look at it and tell what this answer was. When the degree of the top is less than the degree of the bottom, the answer is always 0. When the degree of the top is bigger than the degree of the bottom, the answer is going to either be positive infinity or negative infinity, but you actually have to do the algebra to kind of figure out which infinity you're going to go to. But it's going to be an infinity answer. It's going to be the positive infinity or negative infinity. So that's why I did this problem here. When I take the limit as x approaches, this one I threw negative infinity at you just to see what you guys do with it. And so I got 4x plus 8x cubed divided by 7 minus 18x squared. Well, in this problem, you'll see the degree of the numerator, which is 3, the degree of the denominator is 2, the degree of the top is bigger than the bottom. The answer is going to be either plus or minus infinity, but I don't know which one it's going to be until I do this problem. So I actually have to do the algebra to figure out which one. I got it down to a 50-50 shot. So I'm going to multiply by 1 over x to the degree of the denominator. What's the degree of my denominator? 2. So I'm going to multiply by 1 over x squared for the numerator and 1 over x squared for the denominator. And then I'm going to distribute, multiplying this stuff out. So this is equal to the limit as x approaches negative infinity of 4x times 1 over x squared. Well, one of the x's cancels, thus with 4 over x, plus 8x cubed divided by, or times 1 over x squared. That's 8x cubed over x squared. All the x squareds cancel, but you're left with a single x in the numerator. That reduces down to 8x. Through the denominator, when I distribute, 7 times 1 over x squared is 7 over x squared, minus 18x squared times 1 over x squared is minus 18. The x squareds cancel. So when I take my limit as x approaches, in this case, negative infinity, all my little fractions where x is in the denominator, they all go away and become 0. However, in this problem, there's an extra x left over. This limit as x approaches negative infinity of 8x divided by negative 18. This is what I mean by you gotta have to finish it up and watch the algebra. So now plug in negative infinity. This becomes 8 times negative infinity divided by negative 18. 8 times negative infinity. 8 times something incredibly large, negative. Positive times a negative is a negative. 8 times infinity is infinity. This would be negative infinity. You with me? But when you take negative infinity and divide by negative 18, well, it's infinity divided by 18. That's still going to be infinity, but what is a negative divided by a negative? Positive. So what's the answer going to be? Positive infinity. And that's what I mean by you kind of have to work the problem out and pay attention to the signs of the coefficients to see if you're going to get the positive infinity or you can get the negative infinity. This one, we got the positive infinity. Yeah. This one, the degree of the denominator was x squared, right? So the degree was 2. So I multiplied both the top and bottom by 1 over x squared. This is 1 over x squared divided by 1 over x squared. This is a ratio of 1. So when you multiply by 1 over x squared, 4x times 1 over x squared gives you 4 over x, because just one of the x's cancel. Here, the 8x cubed divided by 1 over x squared, x cubed over x squared gives you that extra x on top, and times the coefficient 8. You multiply by the degree of 1 over x to the degree of the denominator. That's where that 2 came from, right there. Does that make sense? Questions? All right, one last section before that's going to be on your test, which is section 2.5, B. More on continuity. Now, just to remind you guys on continuity here, when you guys were in high school or college algebra or college algebra, algebra 2, algebra even 1, we talked about continuity. And they used a definition way back when, which was still a very, very good definition. The problem is it's not a very mathematical definition. A function is continuous. When I graph it, I don't lift my pencil from the paper when graphing it. That's true, and absolutely true. And when worst comes to worst, keep that guy in the back of your pocket and pull him out when you go, hey, is this guy continuous or not? Well, look at the graph. Did you lift your pencil from your paper when you were plotting the graph out? If you did lift your pencil from the paper and had to go to another little section there, it's called discontinuous. If you don't lift your pencil from the paper, it's called continuous. That's the basic stuff here, but we got to talk about it more mathematically, okay? So, when you don't lift your pencil from the paper, that's called a continuous function. So if the graph of a function has no holes, a hole means I would have to actually lift my pencil from the paper, put the hole in it, and connect it on. Or a jump, that would be one of these piecewise functions where I have to kind of go down here and then it does this. That's called a jump. A vertical asymptote is a line that I can't cross. This is a little dotted line here. So when you're talking about the function that blows up, or maybe it blows down, I'm not sure what either side is going to do, but he can't cross that particular line. So to go from one side to the other, you're going to lift your pencil from the paper to go on the other side. These are all problems with being continuous. So if you don't have either these three, holes, jumps, or vertical asymptotes, then the function is a continuous function. Now, this is the mathematical definition for a function being continuous at a point A. For a function, y equals f of x, to be continuous at x equals a, all the following conditions must be true. Now, this is going to be more mathematical. We have conditions. The first one is, to be continuous, f of a has to exist. So f of a exists. The second one, the limit as x approaches a of f of x exists. Now let's talk about these two guys just for a second. What does it mean when I'm graphing and we have f of a existing? That means I can plug a into my function and I'm not going to get does not exist. I'm going to get a point, which means there's going to be a dot somewhere above a that I'm going to be able to plot. Does that make sense? It's called f of a. I can plot that point. What does it mean for a limit as x approaches a of f of x to exist? And I taught you guys many times already the definition of a function existing, or a limit existing. A limit existing is this. The limit from the left is equal to the limit from the right. When I go from one side and the other, I got to go to the same point. Now there may be a hole there, I don't care. But the fact of the matter is, the limit from one side, in this case, the limit as x approaches a from the left, and the limit as x approaches a from the right. When you look at it, they're going to be going towards the same point. That's what it means for a quote-unquote limit as x approaches a of f of x to exist. And then the third case is this. The limit as x approaches a of f of x has to actually be equal to that f of a. So, let's basically put 2 and 2 together. F of a exists means you're going to have a big old dot right above a. Okay? So when you graph this thing out over here at a, you're going to have a dot. For the limit to exist, that means right here at a, the limit from below is going to be equal to the limit from above. This is where we're talking about the limit exists, over here, L. This is f of a here. This is L. So when I go from below or above, I'm going to the same point, which is L, the limit exists. And then put these two concepts together. When the limit value is equal to the functional value, you get this. So here's my functional value, here's my limit right here, it goes to this point here, but the functional value is the limit, so the dot fills in the hole, and it makes us have continuity. That's the idea behind the definition of a function being continuous. All three of these things have to hold. The f of a has to exist, the limit as x approaches a has to exist, and therefore the limit as x approaches a of f of x has to be equal to f of a. That's what makes continuous at a. Now, getting used to terminology, a function is continuous if it has no points of discontinuity. Points of discontinuity are what prevent a function from being continuous. When I look back up here, there are basically three different types of points of discontinuity. We got holes in the graph, we got jumps, and we got vertical asymptotes. These are the, quote, three cases of points of discontinuity. So if we has no points of discontinuity, we're going to be called continuous. Okay? We don't have any of these guys. All right, and then just for terminology, a function that is discontinuous at any point. If you've got a graph that has a hole in it, a graph that has a jump on it, or a graph that has a vertical asymptote, it's called a discontinuous at any point. And if it's discontinuous at any point, we call the function just called discontinuous. Now, what I really mean by this is this. You know, so now you're beginning to split hairs here, but okay, let me just give you an example here. Here's A, and here comes the function, hits over here, and this point picks up here. So this is what we call a jump, point of discontinuity. But if you look at just this section of the graph keeps on going, the graph is actually continuous on any point less than A. And you keep on going this way, any point bigger than A, the function is also continuous. But there's that one spot where we had to break. And if a function has one point, just one point of discontinuity, we say the function is just discontinuous. Okay? Even though there are going to be sections of being continuous, but in general, we would call, if any function that has one of these points of that causes a point of discontinuity, we just say the function is discontinuous. Okay? Now, terminology. So don't fret, don't freak out, it's just the name of stuff. But remember, we're math people. So with math people, don't think too deep in how we come up with names for stuff. All right, here's the first one, number 5. If the limit as x approaches a of f of x equals L, which doesn't equal f of a, or the limit as x approaches a of f of x equals L and f of a does not exist, there is a hole in the curve at x equals a. This is called a blank blank, okay? So in terms of this, what we got going on is this. We have a hole in the graph. Now, that graph has a hole. Now, sometimes we say the functional value does not exist, or maybe there is a functional value, but the point is actually up here, let's say. Does that make sense? So here's where f of a is, but the rest of the function's down here. So right there at a, it creates a hole in the graph part. Does that make sense? Whether that point exists or doesn't exist, this is still called a hole. And because of this, this is called a removable discontinuity. All right, math people. It looks like somebody took my point and moved it. They removed it from where it was supposed to be on the graph and moved it someplace else. Removable point of discontinuity. Again, don't think in too deep in how we come up with names for stuff in math. Being able to explain it to other people. So this is called a removable discontinuity. Okay? Now, the other one. If the limit as x approaches a from below of f of x does not equal the limit as x approaches a from above or to the right of f of x, then the limit as x approaches a of f of x does not exist. Now that's our definition. We said this before. For a limit to exist, the limit from below has got to be equal to the limit from above. So if you got a point where the limit from below is down here and the limit from above is up here, you're going to two different points. So in drawing that particular concept here, you're going over here like this, and up here it looks like this. Going from the limit as x approaches a from the left is over here at L1. Limit as x approaches a from the right is up here at L2. They're not going to the same thing. By definition, the limit does not exist. Now we call this guy, looks like a jump. This is called a jump. Discontinuity. Because the graph jumps. We're math people, don't think too deep. Okay? Does that make sense? Just giving names for different types of discontinuity. All right? Now, if the limit as x approaches a of f of x is equal to plus or minus infinity, and f of a does not exist, then f is discontinuous at a. This is called a, all right, and we got some names for this guy, so hold on. What we're talking about here is this. For to get plus or minus infinity, remember, by definition, the limit as x approaches a does not exist, because we're not allowed to have an infinity in terms of answers. But we are allowed to have infinity when we do one-sided limits. So what we're talking about here is this. When you take the limit as x approaches a from below of f of x, and you get either plus or minus infinity, and when you take the limit as x approaches a from the right of f of x, and you get either plus or minus infinity, one or the other. Oh, sorry, you can see this. So we're talking about these one-sided limits. The limit as x approaches a from below of f of x equals plus or minus infinity, and the limit as x approaches a from the right of f of x is plus or minus infinity. When you have that, now what does that mean? What does it mean to have an infinity in terms of answers? So here's a. So as I get very, very close to a from below, I'm going to either get positive infinity or negative infinity. Positive infinity means, let's say I blow up. So you get this, okay? As I get close to a, the safe sucker is going to straight up. And let's say when I take the limit as x approaches a from the right, I'm going to get, this time, let's just say it gets negative infinity. It can be either infinity or negative infinity. As I approach a from the right, this thing is going to go straight down, straight down. That's creating a vertical asymptote because the functional value does not exist. That's what we mean by when you get infinity or negative infinity. The only time we are allowed to have an infinity or negative infinity is when we do these one-sided limits. Limit from the left or limit from the right, it's either blowing up or blowing down. Okay? And if you get one of these cases where you blow up on one side and blow up on the other or blow down on the other, this is called a vertical asymptote. Okay? But in terms of the point of discontinuity, we have what we call an infinite discontinuity. Okay? But just to make it similar to the other one, an infinite discontinuity is also known as a non-removable point of discontinuity. Non-removable discontinuity. Again, terminology. Infinite discontinuity, also known as a non-removable. Non-removable is, remember, a removable discontinuity is that hole in the graph thing we were talking about, that little graph with a hole and maybe the point moved away or doesn't exist at all. This one is an infinite discontinuity. In English, that's a vertical asymptote is really what's going on here. Okay? So, here's the deal. Let me break it down for you guys in a very simple way I like to explain stuff. There are basically, there's three different types of discontinuities. And those different types were what? We have basically the hole in the graph. The fancy word for the hole in the graph is a removable discontinuity, also known as a removable singularity if you want to be really fancy in the higher level math stuff. Okay? Removable discontinuity. You have The other one was let's see, we have a vertical asymptote. That vertical asymptote is also known as an infinite discontinuity or non-removable discontinuity. And then you got the third case, which is a jump point of discontinuity, right? How do I recognize these three mathematically? You're going to recognize these three from a limit perspective, okay? A hole in the graph is going to occur when you take a limit as x approaches your a point of f of x, and you end up getting 0 divided by 0. Remember the famous cases of all the limit stuff we were doing? 0 over 0, that traditionally is going to tell you you're going to have a hole in the graph, a removable discontinuity. A vertical asymptote is going to occur when you take your limit as x approaches a from above or below, and you get a number, not 0, a number divided by 0. This is how you know the difference between the two. A hole in the graph is going to be a 0 over 0, a removable discontinuity. A vertical asymptote, called a infinite discontinuity or non-removable discontinuity, is going to be the number divided by 0. And a jump discontinuity is going to occur when you have the famous piecewise function. And you have a particular break right there at a particular point. So give me an example of that would be f of x is equal to something like x squared plus 2 if x is less than 1, and x cubed plus 5 if x is greater than or equal to 1. You see my breaking point on this problem is at 1. When I plug in 1 on the left, I get 1 squared, which is 1 plus 2 is 2. If I plug in the limit as x approaches 1 from the right, that'll be 1 cubed, which is 1 plus 5 is 6. They're not going to the same number. This gives you one of those jump discontinuities. You don't get the same number on both sides of your little breaking of the piecewise function. So this is strategy in terms of how to recognize these things. So when you go to your famous www.hawkstv.com to look for the Hawks version of a worked out example here and on the videos, they did a similar problem like this. And we're going to do lots of problems before because we've got some more problems. But here it is. It says this. Given that x cubed plus x squared minus 4x minus 4 divided by x minus 2. Find the points of discontinuity, if any exist, and determine what type of discontinuity. This is my setup for you guys to figure out what type of discontinuity. There's only 3 types. There's the hole in the graph, there's a vertical asymptote, and then there's the jump. The hole in the graph, fancy word, a removable discontinuity. Vertical asymptote, non-removable discontinuity, or also known as the infinite discontinuity. And a jump discontinuity would show up more like on a piecewise function. You got to check the breaking point. Okay? So, here we go. First part of this thing is real simple. Look at your function. We got the function f of x is equal to x cubed plus x squared minus 4x minus 4 divided by x minus 2. Look at this function, and let's talk about, points of discontinuity are quote-unquote problem points. We're dealing with a lot of fractions with this stuff, and I'm going to have a problem when I divide by what number? 0, when you divide by 0. And so you got to figure out what value of x is going to make you divide by 0. Does that make sense? So since I have division, my problem is going to occur when the x minus 2, the denominator, is actually equal to 0. My problem is at x equals 2. There's where my point of discontinuity is. Does that make sense? So the answer to the problem is, where's the point of discontinuity? We only got one in this problem. It's x equals 2. But now you got to tell me what kind of point it's going to be. To figure out the kind of point, what you do is you take your function and you plug in your problem point into it, and let's see what we get. So let's just do f of 2. This would be equal to 2 cubed plus 2 squared minus 4 times 2 minus 4 divided by 2 minus 2. All right, let's do some basic arithmetic here. 2 cubed is 8. Plus 2 squared is 4. minus 4 times 2 is 8, minus 4 divided by 2 minus 2. Okay, we can do that. 8 plus 4 is 12, minus 8 is 4, minus 4 is 0, divided by clearly 2 minus 2 is 0. But when I plugged in 0, I got 0 over 0. What did that tell me? This one is because it's the hole in the graph, the hole, like you said, but to be fancy on it, this would be a hole in the graph problem, and the term for that is, this one is called a removable discontinuity. Does that make sense? This one is a removable discontinuity. Okay, it's the quote-unquote hole in the graph. It's this case here, the removable discontinuity. This one is the vertical asymptote or non-removable discontinuity, infinite discontinuity, and this is your jump discontinuity. So, that is the answer to the question here. Now take a look at the practice problems here. Same directions. We're supposed to find the quote-unquote problem points. Looking at a function, we've got to find the points that are discontinuous, and then describe what kind they are. And they want you to describe it the mathematical way, okay? We understand the hole in the graph means it's a removable discontinuity. A vertical asymptote means it is a non-removable discontinuity or quote-unquote infinite discontinuity. And the other case is when you get a jump discontinuity, okay? So, take a look at this guy here. F of x is equal to x squared minus x minus 2 divided by x minus 2. Again, where's my problem going to occur at? So I'm going to label it as problem. It's when the denominator is equal to 0. So I'm going to set x minus 2 equal to 0, and I'm going to solve. Add 2 to both sides, and I end up getting x equals 2. There's my problem point. Once again, it's x equals 2. But now to figure out what kind of point of discontinuity this is, I'm going to go back and look at the function and just analyze it. What's f of 2? That'll be 2 squared minus 2 minus 2 over 2 minus 2. 2 squared is 4, minus 2 minus 2 over 2 minus 2. 4 minus 2 is 2, minus 2 is 0 over 0. I got 0 over 0. I mean, I'm going out of my way to show you. I'm literally just plugging this number in. I want to see what the result of this. It's 0 divided by 0. And what does 0 divided by 0 tell me? It's a removable point of discontinuity. Does that make sense? Removable discontinuity. But look at the next one. F of x equals x plus 1 divided by x squared minus 1. All right, once again, identify the problem. The problem is once again going to occur when the denominator, x squared minus 1, is equal to 0. Now, x squared minus 1 is one of these famous difference of square factoring. So x squared minus 1 factors into x plus 1 times x minus 1. Setting equals 0, I said x factor equals 0, x plus 1 equals 0, and x minus 1 equals 0. Subtracting 1 from both sides, I get x equals negative 1. Adding 1 to both sides, I get x equals positive 1. So in this problem, I actually have 2 points of discontinuity. Does that make sense? So we got to analyze it. So for the x equals negative 1 point of discontinuity, I'm going to plug it in. Let's see what type it is. F of negative 1 would be equal to negative 1 plus 1 divided by negative 1 squared minus 1. Negative 1 plus 1 is 0. Negative 1 squared is positive 1. Minus 1 is 0. It's 0 over 0. So x equals negative 1 is what type of point of discontinuity? It is removable. This is a removable discontinuity. Does that make sense? But for this one, you got another point. X equals 1. So to figure out what kind of point of discontinuity this is, you go back and plug it into your function. This would be f of 1, which would be 1 plus 1 divided by 1 squared minus 1. 1 plus 1 is 2. Divided by 1 squared is 1, minus 1 is 0. What is 2 divided by 0? What does that tell me? It's a vertical asymptote, but what's the fancy word for that? non-removable, this is a non-removable discontinuity, also known as, because it does have a secondary name, or you can also say it is an infinite discontinuity. Does that make sense? And you're right, it is a verbalized term. No arguments there, but we're trying to use their terminology. It is a non-removable or infinite discontinuity. Does that make sense? All right, turn the page. We've got more of these things. So, f of x is equal to 2x squared plus 3x minus 1. Where's your problem point? Do you see a fraction in this problem anywhere? Me neither. Which means I got no problems. Problem? No problems. This implies there are no points of discontinuity. What does that actually mean? No points of discontinuity. What kind of function we got here? It's actually continuous. But to answer their question, being honest, they will state the points of discontinuity. There aren't any. None. Does that make sense? This is continuous. But look at D here. F of x is equal to x divided by x squared minus 9. Well, again, this one does have a problem. And your problem occurs with the denominator, x squared minus 9, being equal to 0. X squared minus 9 is the famous difference of squares, so we're going to factor it to x plus 3 times x minus 3 equals 0. Set each factor equals 0, so I get x plus 3 equals 0, and I get x minus 3 equals 0, which tells me x equals negative 3, and x equals positive 3. So this one happens to have 2 points of discontinuity. So we've got to figure out which type they're going to be. So I'm going to come over here and go, okay, x equals negative 3. And when I plug it in, I get f of negative 3 would be equal to negative 3 divided by negative 3 squared minus 9. Well, the numerator stays negative 3, but negative 3 squared is 9 minus 9 is 0. I got a number divided by 0. What does that one tell me? Non-removable or infinite discontinuity. Does that make sense? And then try the other guy, x equals positive 3. But when you try x equals positive 3, f of 3 ends up being 3 divided by 3 squared minus 9, which still becomes 3 in the numerator, but 3 squared is 9 minus 9. So 3 squared is 9, minus 9 is 0. It's 3 divided by 0, which once again tells me that it is a non-removable or infinite point of discontinuity. Does that make sense? So both of these 2 points, 3 and negative 3, are non-removable discontinuities or infinite discontinuities. Does that make sense? Look at E here. F of x is equal to x squared plus 1 if x is less than or equal to 2, and 2x minus 1 if x is greater than 2. This is a piecewise function. But this thing still may be continuous. You got to check him out. If it's going to be discontinuous, if, listen to my words, if it's going to be discontinuous, where would your point of discontinuity be located at? 2. It's the break on your piecewise functions. Okay? But I can't guarantee it's discontinuous yet. I got to check it out. Because this is a piecewise function, what you're going to do here is you're going to take the limit as x approaches your problem, and again, I'm going to state the problem point on the piecewise function. In this case, it's going to be x equals 2. It's the break. It's the 2 right there. So I'm going to take the limit as x approaches 2 from below of f of x and let's see what we get. And I'm going to take the limit as x approaches 2 from above of this function f of x. Now, when I take the limit as x approaches 2 from below, or quote, from the negative side, the left side, I'm slightly less than 2. Because with a piecewise function, you've got to identify which piece you're going to plug into. Since we're plugging in numbers that are, quote, less than 2, do I use the top piecewise function or the bottom piecewise function? Top. So I'm going to use the top one. So this will be equal to the limit as x approaches 2 from below of x squared plus 1, the one on top. And then first rule of 11, plug it in. This will be 2 squared plus 1, and 2 squared is 4 plus 1 is 5. So I get 5 for that part. Now I'm going to take the limit as x approaches 2 from the right. I'm slightly bigger than 2. Since I'm bigger than 2, I plug it into the bottom piecewise function. So this will be the limit as x approaches 2 from the right of 2x minus 1. Using that function, the first rule of limits is plug it in. This will be 2 times 2 minus 1. 2 times 2 is 4 minus 1 is 3. They're not equal to each other. Because this could have been continuous if the limit from left equals the limit from right, which is equal to the functional value. All those guys happen to line up. This is continuous. But what we got here is the limit as x approaches 2 from the left is up here at 5. The limit as x approaches 2 from the right is down here at 3. They're not going to the same point. What do we call that guy? So therefore, x equals 2 is a jump. Discontinuity. Does that make sense? This one, it would be what we call a jump. Again, real recognition is the fact it was a piecewise function, so that's traditionally where these guys are going to show up at. And because the limit from the left doesn't equal the limit right from the right, this will be what we call a jump discontinuity. Does that make sense? Look at this next problem. It says this. Find a value k so that f of x is equal to x squared plus 3x divided by x if x is less than 0, and 2x squared minus k if x is greater than or equal to 0 will be continuous at your problem point x equals 0. See, you got this unknown here, k, and it's a piecewise function. So I have a problem that 0 could possibly be a point of discontinuity. They want us to find the value of k that's actually going to make this guy continuous. Now, the problem with a piecewise function is these jump discontinuities, but here's the problem. See, when I look at the limit as x approaches 2 in this last example, it doesn't exist. But to be continuous, that limit has to exist. It's going to have to be equal to the functional value. So to figure out a problem like this, it's real simple. This is what you do. You take your problem point, and you take the limit as x approaches that problem point. This will be 0 from the left of f of x. And you're going to take the limit as x approaches 0 from the right of f of x. And you're going to see what you get. But to force the limit as x approaches 0 of f of x to exist, the big deal is that these two guys have to be what? The limit from the left and the limit from the right, for the limit to exist, have to go to the same number. So the trick is going to be, at the end of the day, for the limit to exist, these guys have to be equal to each other. That's the game plan. So here we go. Take the limit as x approaches 0 from the left of f of x. That'll be equal to the limit as x approaches 0 from the left. To the left of 0 means I'm slightly less than 0, and since I'm less than 0, I plug it into the top piecewise function, x squared plus 3x divided by x. Now we do this problem. What's the first rule of limits? Plug it in. And when I plug in 0, 0 squared is 0, 3 times 0 is 0, 0 plus 0 is 0, divided by 0. And when I'm doing a limit that's 0 divided by 0, I'm going to do algebra. I'm going to clean this thing up. I'm going to try to cancel something out. And to cancel something out, I want to be able to strict multiplication division. What do I have in common in that numerator? X. So I'm going to factor it out. So this would be equal to the limit as x approaches 0 from below of x times x plus 3 divided by x. And so what happens to the x's here? They cancel. This will be equal to the limit as x approaches 0 from the left of x plus 3. I clean it up, and then after you cancel, you plug in the number again. And when I plug it in, I don't write limit anymore. So this will be 0, basically from the left, plus 3. But 0 plus 3 is 3. So the limit as x approaches 0 from the left of f of x is equal to 3. Now, we're going to take the limit as x approaches 0 from the right of f of x. This will be equal to the limit as x approaches 0 from the right of, I'm slightly bigger than 0, to the right of 0, so bigger than 0, I plug it into the equation 2x squared minus k. And the first rule of limits is to do what? Plug it in, but be careful. This is where most of it screwed up. Plug it in for what letter? What letter are we going to plug 0 in for? X. K is a constant. That's what we're supposed to find. So I'm going to replace x with zeros. This will give me 2 times 0 squared minus k. And 0 squared is 0. 2 times 0 is 0. So that just gives you pretty much minus k. And therefore, for the limit to exist, therefore, for the limit to exist and this function to be continuous, the negative k has got to be equal to 3. You've got to set these two guys equal to each other. That's what's going to force it to be continuous. Does that make sense? So when the limit from left equals number from right, you don't actually have a jump anymore. You're going to merge these two guys together, so there's no jump. They actually meet up to each other. So solve for k here. Negative k equals 3. What am I going to do? Divide by negative 1. So what is my answer to my problem? K equals what? 3 divided by negative 1 is, you got it, negative 3. And I think I put a problem like this on your homework set. So pay attention to it, but here's the trick. Take the limit from the left, take the limit from the right, crunch it out, and there's going to be this constant that you're going to have in one of your functions. And set them equal to each other and then solve for that constant, and that makes the function continuous. Does that make sense? I'll lose you guys anywhere. Now, you know at the end of chapter 2, at the end of each chapter from this point on, into chapter 2, chapter 3, chapter 4, chapter 5, and chapter 6, we have in our notebook, we have problems you should practice. These are still great problems. Now, I'm doing something a little different. I am actually making you guys homework sets that are going to mimic the test. And I put a little column in there. They're called test review / homework sets. And I'll talk more about those next time. But your first one is due on Friday. But that doesn't mean you shouldn't be doing this stuff. This is great review. So I've got 3 minutes left in class here. So let's do it. Okay, so 3 minutes. Well, how much minutes do I have? What time is it? 1:05? Well, I'm actually, 50 minutes. Yeah, an hour. Okay, I got 3 minutes left in class. Question though? Yeah. Now, that's because when you set up any kind of test thing in Canvas, the automatic default, everything is due at 8 a.m. Don't worry about it. See, you understand, in the Canvas thing, I got to have a column for where I'm going to put the test grades and stuff. So don't worry about that. It's just the automatic default of Canvas when I set up the particular test and stuff. And remember, our test is going to be on Monday, but it's not at 8 o'clock in the morning. It's at 9:05. But you should try to get here a little early, because I'm going to try to get here a little early. I know Dr. Burnap's in class here, but once I can throw those guys out of here, I'll start passing out the test. As soon as the test is passed out, you can start taking it, okay? All right, so take a look at this guy. I got a couple of seconds. We can do a problem. Take the limit as x approaches -4 from below of f of x. So this is a piecewise function, so this is going to be the limit as x approaches -4 from the left. Which piece of my piecewise function do I use, the top or bottom? Top. So the top function is -2x plus 8, and the first rule of limits is to do what? Plug it in. This will be -2 times x is going to -4 from the left, but that's -4 plus 8. 2 times -2 times -4 is positive 8 plus 8. The answer is 16. What is the limit as x approaches -4 from the right? That means I'm slightly bigger than 4. So when I take the limit as x approaches -4 from the right, I'm going to plug it into which function, top or bottom? the bottom one, bigger than 4, that'll be x plus 8 divided by x plus 4. Okay, and here's the deal. This is remember, this is a one-sided piecewise function here. So when you plug it in, I'm going to get negative 4 plus 8 divided by negative 4 plus 4. That is going to be 4 divided by 0, but be careful because it's a one-sided. That tells me my answer is either going to be positive infinity or negative infinity. If this was a full limit, what would the answer be? Number divided by 0 on a full limit does not exist. But because this is a one-sided limit, we do expect you guys to tell us, okay, if it's one-sided, it's either got to blow up or blow down. Which way is it going to go? How do I figure that out? Let's do a d-bar. And so x and y, we're going after negative 4 from the right. From the right means we're slightly bigger than negative 4. So what kind of numbers am I going to plug in? Negative 3.9 and negative 3.99. All you need is a couple of points here, because you know the answer. You got to just tell me if it's going to blow up or is it going to blow down. But remember, this where most people mess this up is, you think of negative 4, here's negative 5, and here's negative 3. On the right side, negative 4 on the right is coming in this way. That's slightly bigger than negative 4, but when we're talking about negative, that's on the negative 3 side. That's why I use negative 3.9 and stuff like that. So here we go. Plugging it in. Plugging in negative 3.9, parentheses. Negative 3.9 plus 8 divided by, parentheses, negative 3.9 plus 4. What number did I get? I got 41. Now, plug in negative 3.99. So just call it back down again. Insert an extra 9 there. So this is now, I'm plugging negative 3.99 into this guy. And what do I get? 401. Well, that pretty much tells me where I'm going. If I'm going from negative 4 on the right, where's my function going towards? Positive infinity. So the answer to this problem is positive infinity. So the limit on the left was was 16. The limit on the right was 4. Does that make sense? Did I lose you guys anywhere? Okay. We'll do more of these problems next time, but the focus that I'm going to have on Friday's class is I'm going to do your homework set. But do practice these problems. And if you've got a question, bring it to class. I'll be more than happy to do it. Make sure you get your questions answered and stuff. And I'll see you guys on Friday.